Radioactive decay.
Radioactive decay, also known as nuclear decay or radioactivity, is the process by which a nucleus of an unstable atom loses energy by emitting particles of ionizing radiation. A material that spontaneously emits this kind of radiation, which includes the emission of energetic alpha particles, beta particles, and gamma rays, is considered radioactive. Radioactive decay is a stochastic, that is random, process at the level of single atoms, in that, according to quantum theory, it is impossible to predict when a particular atom will decay. However, the chance that a given atom will decay is constant over time. For a large number of atoms, the decay rate for the collection is computable from the measured decay constants of the nuclides, or equivalently from the half-lives. There are many different types of radioactive decay, see table below. A decay, or loss of energy, results when an atom with one type of nucleus, called the parent radionuclide, or parent radioisotope, transforms into an atom with a nucleus in a different state, or to a different nucleus containing different numbers of protons and neutrons. Either of these products is named the daughter nuclide. In some decays, the parent and daughter are different chemical elements, and thus the decay process results in nuclear transmutation, creation of an atom of a different element. The first decay processes to be discovered were alpha decay, beta decay, and gamma decay. Alpha decay occurs when the nucleus ejects an alpha particle, helium nucleus. This is the most common process of emitting nucleons, but in rarer types of decays, nuclei can eject protons, or specific nuclei of other elements, in the process called cluster decay. Beta decay occurs when the nucleus emits an electron or positron and a type of neutrino, in a process that changes a proton to a neutron or the other way around. The nucleus may capture an orbiting electron, converting a proton into a neutron, electron capture. All of these processes result in nuclear transmutation. By contrast, there are radioactive decay processes that do not result in transmutation. The energy of an excited nucleus may be emitted as a gamma ray in gamma decay, or used to eject an orbital electron by interaction with the excited nucleus, in a process called internal conversion. Highly excited neutron-rich radioisotopes, formed as the product of other types of decay, occasionally lose energy by emitting neutrons, and this results in a change in an element from one isotope to another. Another type of radioactive decay results in products that are not defined, but appear in a range of pieces of the original nucleus. This decay, which is called spontaneous fission, happens when a large unstable nucleus spontaneously splits into two, and occasionally three, smaller daughter nuclei, and generally immediately emits gamma rays, neutrons, or other particles as a consequence. For a summary table showing the number of stable and radioactive nuclides in each category, see radionuclide. There are 34 mildly radioactive elements on Earth that are primordial nuclides, that is still decaying from the formation of the Solar System. Well-known examples are uranium and thorium. Another 50 or so radionuclides can be detected in decay chains resulting from the primordial nuclides, such as radium and radon, and also new cosmogenic processes, for example carbon-14. Radionuclides can also be produced artificially, for example using particle accelerators or nuclear reactors, with about 650 of these characterized with half-lives over an hour, and several thousand more characterized with even shorter half-lives. See list of nuclides for a list by half-life.
Discovery and history.
It has been claimed that radioactivity was discovered by Abel Neeb de Saint Victor in 1857. But this was not well publicized and was soon forgotten. Radioactivity was rediscovered in 1896 by the French scientist Henri Becquerel, while working on phosphorescent materials. These materials glow in the dark after exposure to light, and he suspected that the glow produced in cathode ray tubes by X-rays might be associated with phosphorescence. He wrapped a photographic plate in black paper and placed various phosphorescent salts on it. All results were negative until he used uranium salts. The result with these compounds was a blackening of the plate. These radiations were called Becquerel rays. It soon became clear that the blackening of the plate had nothing to do with phosphorescence, because the plate blackened when the mineral was in the dark. Non-phosphorescent salts of uranium and metallic uranium also blackened the plate. It was clear that there was a form of radiation that could pass through paper and was causing the plate to become black. At first, it seemed that the new radiation was similar to the then recently discovered X-rays. Further research by Becquerel, Ernest Rutherford, Paul Villard, Pierre Curie, Marie Curie, and others discovered that this form of radioactivity was significantly more complicated. Different types of decay can occur, producing very different types of radiation. Rutherford was the first to realize that they all occur in accordance with the same mathematical exponential formula, see below, and Rutherford and his student Frederick Soddy were the first to realize that many decay processes resulted in the transmutation of one element to another. Subsequently, the radioactive displacement law of Fajans-Soddy was formulated to describe the products of alpha and beta decay. The early researchers also discovered that many other chemical elements besides uranium have radioactive isotopes. A systematic search for the total radioactivity in uranium ores also guided Pierre and Marie Curie to isolate two new elements, polonium and radium. The chemical similarity of radium to barium made these two elements difficult to distinguish, except for the radioactivity of radium. The discovery of radioactive elements in the 1890s opened the way for new dating techniques that suggested an age for Earth of several billion years.
Types of decay.
As for types of radioactive radiation, it was found that an electric or magnetic field could split such emissions into three types of beams. The rays were given the alphabetic names alpha, beta, and gamma, in order of their ability to penetrate matter. While alpha decay was seen only in heavier elements, atomic number 52, tellurium, and greater, the other two types of decay was seen in all of the elements. Lead, atomic number 82, is the heaviest element to have any isotope stable, to the limit of measurement, to radioactive decay. Radioactive decay is seen in all isotopes of all elements of atomic number 83, bismuth, or greater. Bismuth, however, is only very slightly radioactive. In analyzing the nature of the decay products, it was obvious from the direction of electromagnetic forces induced on the radiations by external magnetic and electric fields that alpha particles from decay carried a positive charge, beta particles carried a negative charge, and gamma rays were neutral. From the magnitude of deflection, it was clear that alpha particles were much more massive than beta particles. Passing alpha particles through a very thin glass window and trapping them in a discharge tube allowed researchers to study the emission spectrum of the resulting gas, and ultimately proved that alpha particles are helium nuclei. Other experiments showed the similarity between classical beta radiation and cathode rays, they are both streams of high-speed electrons. Likewise, gamma radiation and X-rays were found to be similar high-energy electromagnetic radiation. The relationship between the types of decays also began to be examined. For example, gamma decay was almost always found to be associated with other types of decay, and occurred at about the same time, or afterwards. Gamma decay is a separate phenomenon, with its own half-life, now termed isomeric transition, was found in natural radioactivity to be a result of the gamma decay of excited metastable nuclear isomers, which were, in turn, created from other types of decay. Although alpha, beta, and gamma radiations were most commonly found, other types of decay were eventually discovered. Shortly after the discovery of the positron in cosmic ray products, it was realized that the same process that operates in classical beta decay can also produce positrons, positron emission. In an analogous process, instead of emitting positrons and neutrinos, some proton-rich nuclides were found to capture their own atomic electrons, electron capture, and emit only a neutrino, and usually also a gamma ray. Each of these types of decay involves the capture or emission of nuclear electrons or positrons, and acts to move a nucleus toward the ratio of neutrons to protons that has the least energy for a given total number of nucleons, neutrons plus protons. A theoretical process of positron capture, analogous to electron capture, is possible in antimatter atoms, but has not been observed since the complex antimatter atoms are not available. This would require antimatter atoms at least as complex as beryllium-7, which is the lightest known isotope of normal matter to undergo decay by electron capture. Shortly after the discovery of the neutron in 1932, Enrico Fermi realized that certain rare beta decay reactions immediately yield neutrons as a decay particle, neutron emission. Isolated proton emission was eventually observed in some elements. It was also found that some heavy elements may undergo spontaneous fission into products that vary in composition. In a phenomenon called cluster decay, specific combinations of neutrons and protons other than alpha particles, helium nuclei, were found to be spontaneously emitted from atoms. Other types of radioactive decay that emit previously seen particles were found, but by different mechanisms. An example is internal conversion, which results in electron, and sometimes high-energy photon, emission. Even though it involves neither beta nor gamma decay, a neutrino is not emitted, and neither the electron nor photon originate in the nucleus. Internal conversion decay, like isomeric transition gamma decay and neutron emission, involves an excited nuclide releasing energy, without transmutation of one element into another. Rare events that involve a combination of two beta decay type events happening simultaneously, see below, are known. Any decay process that does not violate the conservation of energy or momentum laws, and perhaps other particle conservation laws, is permitted to happen, although not all have been detected. An interesting example, discussed in a final section, is bound-state beta decay of rhenium-187. In this process, an inverse of electron capture, beta electron decay of the parent nuclide is not accompanied by beta electron emission, because the beta particle has been captured into the K shell of the emitting atom. An entire neutrino, however, is emitted.
Danger of radioactive substances.
The dangers of radioactivity and radiation were not immediately recognized. The discovery of X-rays in 1895 led to widespread experimentation by scientists, physicians, and inventors. Many people began recounting stories of burns, hair loss and worse in technical journals as early as 1896. In February of that year, Professor Daniel and Dr. Dudley of Vanderbilt University performed an experiment involving X-raying Dudley's head that resulted in him losing his hair under where the tube was placed, reported in the X-Rays Science News supplement. A report by Dr. H. D. Hawkes, a graduate of Columbia College, of his suffering severe hand and chest burns in an X-ray demonstration, was the first of many other reports in Electrical Review. Many experimenters including Ellie Thompson at Thomas Edison's lab, William J. Morton, and Nikola Tesla also reported burns. Ellie Thompson deliberately exposed a finger to an X-ray tube over a period of time and suffered pain, swelling, and blistering. Other effects were sometimes blamed for the damage, including ultraviolet rays and, according to Tesla, ozone. Many physicians claimed that there were no effects from X-ray exposure at all. The genetic effects of radiation, including the effect of cancer risk, were recognized much later. In 1927, Hermann Joseph Muller published research showing genetic effects and, in 1946, was awarded the Nobel Prize for his findings. Before the biological effects of radiation were known, many physicians and corporations began marketing radioactive substances as patent medicine in the form of glow-in-the-dark pigments. Examples were radium enema treatments, and radium-containing waters to be drunk as tonics. Marie Curie protested against this sort of treatment, warning that the effects of radiation on the human body were not well understood. Curie later died from aplastic anemia, likely caused by exposure to ionizing radiation. By the 1930s, after a number of cases of bone necrosis and death of enthusiasts, radium-containing medicinal products had been largely removed from the market. Radioactive quackery.
Radioactive decay rates.
The decay rate, or activity, of a radioactive substance is characterized by constant quantities. The half-life, T1/2, is the time taken for the activity of a given amount of a radioactive substance to decay to half of its initial value. See list of nuclides. The decay constant, L, lambda the inverse of the mean lifetime, the mean lifetime, T, tau the average lifetime of a radioactive particle before decay. Although these are constants, they are associated with statistically random behavior of populations of atoms. In consequence, predictions using these constants are less accurate for small number of atoms. In principle, the reciprocal of any number greater than 1, a half-life, a third life, or even a 1/2 life, can be used in exactly the same way as half-life. But the half-life T1/2 is adopted as the standard time associated with exponential decay. Time variable quantities. Total activity, A, is the number of decays per unit time of a radioactive sample. Number of particles, N, is the total number of particles in the sample. Specific activity, SA, number of decays per unit time per amount of substance of the sample at time set to 0, T equals 0. Amount of substance can be the mass, volume or moles of the initial sample. These are related as follows. Where NO is the initial amount of active substance, substance that has the same percentage of unstable particles as when the substance was formed.
Units of radioactivity measurements.
The SI unit of radioactive activity is the becquerel, in honor of the scientist Henri Becquerel. 1 becquerel is defined as 1 transformation, or decay or disintegration, per second. Since sensible sizes of radioactive material contains many atoms, a becquerel is a tiny measure of activity. Amounts giving activities on the order of GBq, gigabecquerel, 1x109 decays per second, or TBq, terabecquerel, 1x1012 decays per second, are commonly used. Another unit of radioactivity is the Curie, psi, which was originally defined as the amount of radium emanation, radon-222, in equilibrium with 1 gram of pure radium, isotope Ra-226. At present it is equal, by definition, to the activity of any radionuclide decaying with a disintegration rate of 3.7 x 1010 becquerel, so that 1 Curie, psi, equals 3.7 x 1010 becquerel. The use of psi is currently discouraged by the SI. Low activities are also measured in disintegrations per minute, dpm.
Mathematics of radioactive decay. Universal law of radioactive decay.
Radioactivity is one very frequent example of exponential decay. The law describes the statistical behavior of a large number of nuclides, rather than individual ones. In the following formalism, the number of nuclides or nuclide population N, is of course a discrete variable, a natural number, but for any physical sample N is so large, amounts of L equals 1023, Avogadro's constant, that it can be treated as a continuous variable. Differential calculus is needed to set up differential equations for modeling the behavior of the nuclear decay.
1 decay process.
Consider the case of a nuclide A decaying into another B by some process A, B, emission of other particles, like electron neutrinos northeast and electrons E and beta decay, are irrelevant in what follows. The decay of an unstable nucleus is entirely random and it is impossible to predict when a particular atom will decay. However, it is equally likely to decay at any time. Therefore, given a sample of a particular radioisotope, the number of decay events dn expected to occur in a small interval of time dt is proportional to the number of atoms present n, that is. Particular radionuclides decay at different rates, so each has its own decay constant L. The expected decay dnn is proportional to an increment of time, dt. The negative sign indicates that n decreases as time increases, as the decay events follow one after another. The solution to this first-order differential equation is the function where NO is the value of n at time t equals 0. We have for all time t, where n total is the constant number of particles throughout the decay process, clearly equal to the initial number of A nuclides since this is the initial substance. If the number of non-decayed A nuclei is, then the number of nuclei of B, that is number of decayed A nuclei, is the number of decays observed over a given interval obeys Poisson's statistics. If the average number of decays is less than or greater than, the probability of a given number of decays n is.
Chain decay processes.
Chain of two decays. Now consider the case of a chain of two decays, one nuclide A decaying into another B by one process, then re-decaying into another C by a second process, that is, A, B, C. The previous equation cannot be applied to the decay chain, but can be generalized as follows. Since A decays into B, then re-decays into C, the activity of A adds to the total number of B nuclides in the present sample, before those B nuclides decay and reduce the number of nuclides leading to the later sample. In other words, the number of second-generation nuclei B increases as a result of a first-generation nuclei decay of A, and decreases as a result of its own decay into the third-generation nuclei C. The sum of these two terms gives the law for a decay chain for two nuclides. The rate of change of Nb, that is dNb dt, is related to the changes in the amounts of A and B. Nb can increase as B is produced from A and decrease as B produces C. Rewriting using the previous results. The subscripts simply refer to the respective nuclides, that is Na is the number of nuclides of type A, NaO is the initial number of nuclides of type A, La is the decay constant for A, and similarly for nuclide B. Solving this equation for Nb gives. Naturally, this equation reduces to the previous solution. In the case B is a stable nuclide, Lb equals 0. As shown above for one decay. The solution can be found by the integration factor method, where the integrating factor is Lbt. This case is perhaps the most useful, since it can derive both the one-decay equation, above, and the equation for multi-decay chains, below, more directly. Chain of any number of decays. For the general case of any number of consecutive decays in a decay chain, that is, A1, A2 IAD, where D is the number of decays and I is a dummy index, I equals 1, 2, 3. D. Each nuclide population can be found in terms of the previous population. In this case N2 equals 0, N3 equals 0, Nd equals 0. Using the above result in a recursive form. The general solution to the recursive problem are given by Bateman's equations.
Alternative decay modes.
In all of the above examples, the initial nuclide decays into only one product. Consider the case of one initial nuclide which can decay into either of two products, that is A, B and A, C in parallel. For example, in a sample of potassium-40, 89.3% of the nuclei decay to calcium-40 and 10.7% to argon-40. We have for all time T, which is constant, since the total number of nuclides remains constant. Differentiating with respect to time. Defining the total decay constant L in terms of the sum of partial decay constants Lb and Lc. Notice that. Solving this equation for Na, where NaO is the initial number of nuclide A. When measuring the production of one nuclide, one can only observe the total decay constant L. The decay constants Lb and Lc determine the probability for the decay to result in products B or C as follows. Because the fraction pound per liter of nuclei decay into B while the fraction LCl of nuclei decay into C.
Corollaries of the decay laws.
The above equations can also be written using quantities related to the number of nuclide particles n in a sample. The activity, A equals Ln, the amount of substance, N equals NL, the mass, M equals N equals ARNL. Where L equals 6.022 x 1023 is Avogadro's constant, R is the relative atomic mass number, and the amount of the substance is in moles.
Decay timing, definitions and relations. time constant and mean life.
For the 1 decay solution A, B. The equation indicates that the decay constant L has units of T1, and can thus also be represented as 1 per ton, where T is a characteristic time of the process called the time constant. In a radioactive decay process, this time constant is also the mean lifetime for decaying atoms. Each atom lives for a finite amount of time before it decays, and it may be shown that this mean lifetime is the arithmetic mean of all the atoms' lifetimes, and that it is T, which again is related to the decay constant as follows. This form is also true for 2 decay processes simultaneously A, B plus C, inserting the equivalent values of decay constants, as given above. Into the decay solution leads to
Half-life.
A more commonly used parameter is the half-life. Given a sample of a particular radionuclide, the half-life is the time taken for half the radionuclide's atoms to decay. For the case of 1 decay nuclear reactions, the half-life is related to the decay constant as follows: set n equals NO/2 and T equals T1/2 to obtain. This relationship between the half-life and the decay constant shows that highly radioactive substances are quickly spent, while those that radiate weakly endure longer. Half-lives of known radionuclides vary widely, from more than 10-19 years, such as for the very nearly stable nuclide 209B, to 10-23 seconds for highly unstable ones. The factor of Ln, 2, in the above relations results from the fact that concept of half-life is merely a way of selecting a different base other than the natural base E for the lifetime expression. The time constant T is the E-1 life, the time until only 1/E remains, about 36.8%, rather than the 50% in the half-life of a radionuclide. Thus, T is longer than T1/2. The following equation can be shown to be valid. Since radioactive decay is exponential with a constant probability, each process could as easily be described with a different constant time period that, for example, gave its 1/3 life, how long until only January 3rd is left, or 1/10 life, a time period until only 10% is left, and so on. Thus, the choice of T and T1/2 for marker times are only for convenience, and from convention. They reflect a fundamental principle only in so much as they show that the same proportion of a given radioactive substance will decay, during any time period that one chooses. Mathematically, the nth life for the above situation would be found in the same way as above, by setting n equals NO/n, 1 and substituting into the decay solution to obtain.
Example:
A sample of 14C, whose half-life is 57-30 years, has a decay rate of 14 disintegration per minute, dpm, per gram of natural carbon. An artifact is found to have radioactivity of 4 dpm per gram of its present C. How old is the artifact? Using the above equation, we have where
changing decay rates.
The radioactive decay modes of electron capture and internal conversion are known to be slightly sensitive to chemical and environmental effects which change the electronic structure of the atom, which in turn affects the presence of 1s and 2s electrons that participate in the decay process. A small number of mostly light nuclides are affected. For example, chemical bonds can affect the rate of electron capture to a small degree, in general, less than 1% depending on the proximity of electrons to the nucleus. In 7b, a difference of 0.9% has been observed between half-lives in metallic and insulating environments. This relatively large effect is because beryllium is a small atom whose valence electrons are in 2s atomic orbitals, which are subject to electron capture in 7b because, like all s atomic orbitals in all atoms, they naturally penetrate into the nucleus. In 1992, Leung et al. Of the Darmstadt Heavy Ion Research Group observed an accelerated B decay of 163 dy66+. Although neutral 163 dy is a stable isotope, the fully ionized 163Dy66 undergoes B decay into the K and L shells with a half-life of 47 days. Rhenium-187 is another spectacular example. 187Re normally beta decays to 187Os with a half-life of 41.6 x 109 years, but studies using fully ionized 187Re atoms, bare nuclei, have found that this can decrease to only 33 years. This is attributed to bound state B decay of the fully ionized atom. The electron is emitted into the K shell, one's atomic orbital, which cannot occur for neutral atoms in which all low-lying bound states are occupied. A number of experiments have found that decay rates of other modes of artificial and naturally occurring radioisotopes are, to a high degree of precision, unaffected by external conditions such as temperature, pressure, the chemical environment, and electric, magnetic, or gravitational fields. Comparison of laboratory experiments over the last century. Studies of the Oklo natural nuclear reactor, which exemplified the effects of thermal neutrons on nuclear decay, and astrophysical observations of the luminosity decays of distant supernovae, which occurred far away so the light has taken a great deal of time to reach us, for example, strongly indicate that decay rates have been constant, at least to within the limitations of small experimental errors, as a function of time as well. Recent results suggest the possibility that decay rates might have a weak dependence on environmental factors. It has been suggested that measurements of decay rates of silicon-32, manganese-54, and radium-226 exhibit small seasonal variations, of the order of 0.1%, while the decay of radon-222 exhibit large 4% peak-to-peak seasonal variations, proposed to be related to either solar flare activity or distance from the Sun. However, such measurements are highly susceptible to systematic errors, and a subsequent paper has found no evidence for such correlations in 7 other isotopes, 22 Na, 44T, 108 Ag, 121 Sn, 133 Ba, 241 Am, 238 Pu, and sets upper limits on the size of any such effects.
Theoretical basis of decay phenomena.
The neutrons and protons that constitute nuclei, as well as other particles that approach close enough to them, are governed by several interactions. The strong nuclear force, not observed at the familiar macroscopic scale, is the most powerful force over subatomic distances. The electrostatic force is almost always significant, and, in the case of beta decay, the weak nuclear force is also involved. The interplay of these forces produces a number of different phenomena in which energy may be released by rearrangement of particles in the nucleus, or else the change of one type of particle into others. These rearrangements and transformations may be hindered energetically, so that they do not occur immediately. In certain cases, random quantum vacuum fluctuations are theorized to promote relaxation to a lower energy state, the decay in a phenomenon known as quantum tunneling. Radioactive decay half-life of nuclides has been measured over timescales of 55 orders of magnitude, from 2.3 x 10^23 seconds, for hydrogen-7, to 6.9 x 10^31 seconds, for tellurium-128. The limits of these timescales are set by the sensitivity of instrumentation only, and there are no known natural limits to how brief or long a decay half-life a radioactive decay of a radionuclide may be. The decay process, like all hindered energy transformations, may be analogized by a snow field on a mountain. While friction between the ice crystals may be supporting the snow's weight, the system is inherently unstable with regard to a state of lower potential energy. A disturbance would thus facilitate the path to a state of greater entropy. The system will move towards the ground state, producing heat, and the total energy will be distributable over a larger number of quantum states. Thus, an avalanche results. The total energy does not change in this process, but, because of the second law of thermodynamics, avalanches have only been observed in one direction, and that is toward the ground state, the state with the largest number of ways in which the available energy could be distributed. Such a collapse, a decay event, requires a specific activation energy. For a snow avalanche, This energy comes as a disturbance from outside the system, although such disturbances can be arbitrarily small. In the case of an excited atomic nucleus, the arbitrarily small disturbance comes from quantum vacuum fluctuations. A radioactive nucleus, or any excited system in quantum mechanics, is unstable, and can, thus, spontaneously stabilize to a less excited system. The resulting transformation alters the structure of the nucleus and results in the emission of either a photon or a high-velocity particle that has mass, such as an electron, alpha particle, or other type.
Occurrence and applications.
According to the Big Bang theory, stable isotopes of the lightest 5 elements, H, He, and traces of Li, B, and B, were produced very shortly after the emergence of the universe, in a process called Big Bang nucleosynthesis. These lightest stable nuclides, including deuterium, survive to today, but any radioactive isotopes of the light elements produced in the Big Bang, such as tritium, have long since decayed. Isotopes of elements heavier than boron were not produced at all in the Big Bang, and these first 5 elements do not have any long-lived radioisotopes. Thus, all radioactive nuclei are, therefore, relatively young with respect to the birth of the universe, having formed later in various other types of nucleosynthesis in stars, in particular, supernovae, and also during ongoing interactions between stable isotopes and energetic particles. For example, carbon-14, a radioactive nuclide with a half-life of only 57–30 years, is constantly produced in Earth's upper atmosphere due to interactions between cosmic rays and nitrogen. Nuclides that are produced by radioactive decay are called radiogenic nuclides, whether they themselves are stable or not. There exist stable radiogenic nuclides that were formed from short-lived extinct radionuclides in the early Solar System. The extra presence of these stable radiogenic nuclides, such as Xi-129 from primordial I-129, against the background of primordial stable nuclides can be inferred by various means. Radioactive decay has been put to use in the technique of radioisotopic labeling, which is used to track the passage of a chemical substance through a complex system, such as a living organism. A sample of the substance is synthesized with a high concentration of unstable atoms. The presence of the substance in one or another part of the system is determined by detecting the locations of decay events. On the premise that radioactive decay is truly random, rather than merely chaotic, it has been used in hardware random number generators. Because the process is not thought to vary significantly in mechanism over time, it is also a valuable tool in estimating the absolute ages of certain materials. For geological materials, the radioisotopes and some of their decay products become trapped when a rock solidifies, and can then later be used, subject to many well-known qualifications, to estimate the date of the solidification. These include checking the results of several simultaneous processes and their products against each other, within the same sample. In a similar fashion, and also subject to qualification, the rate of formation of carbon-14 in various eras, the date of formation of organic matter within a certain period related to the isotope's half-life may be estimated, because the carbon-14 becomes trapped when the organic matter grows and incorporates the new carbon-14 from the air. Thereafter, the amount of carbon-14 in organic matter decreases according to decay processes that may also be independently cross-checked by other means, such as checking the carbon-14 in individual tree rings, for example.
Origins of radioactive nuclides.
Radioactive primordial nuclides found in the Earth are residues from ancient supernova explosions which occurred before the formation of the Solar System. They are the long-lived fraction of radionuclides surviving in the primordial solar nebula through planet accretion until the present. The naturally occurring short-lived radiogenic radionuclides found in rocks are the daughters of these radioactive primordial nuclides. Another minor source of naturally occurring radioactive nuclides are cosmogenic nuclides, formed by cosmic ray bombardment of material in the Earth's atmosphere or crust. The radioactive decay of these radionuclides in rocks within Earth's mantle and crust contributes significantly to Earth's internal heat budget.
Decay modes in table form.
Radionuclides can undergo a number of different reactions. These are summarized in the following table. A nucleus with mass number A and atomic number Z is represented as A, Z. The column daughter nucleus indicates the difference between the new nucleus and the original nucleus. Thus, A 1, Z, means that the mass number is 1 less than before, but the atomic number is the same as before. Radioactive decay results in a reduction of some rest mass, once the released energy, the disintegration energy, has escaped in some way. For example, the products might be captured and cooled, and the heat allowed to escape. Although decay energy is sometimes defined as associated with the difference between the mass of the parent nuclide products and the mass of the decay products, this is true only of rest mass measurements, where some energy has been removed from the product system. This is true because the decay energy must always carry mass with it, wherever it appears. See mass in special relativity, according to the formula E equals mc2. The decay energy is initially released as the energy of emitted photons plus the kinetic energy of massive emitted particles, that is, particles that have rest mass. If these particles come to thermal equilibrium with their surroundings and photons are absorbed, then the decay energy is transformed to thermal energy, which retains its mass. Decay energy therefore remains associated with a certain measure of mass of the decay system, called invariant mass, which does not change in the decay, even though the energy of decay is distributed among decay particles. The energy of photons, the kinetic energy of emitted particles, and, later, the thermal energy of the surrounding matter, all contribute to the invariant mass of the system. Thus, while the sum of rest masses of particles is not conserved in radioactive decay, the system mass and system invariant mass, and also the system total energy, is conserved throughout any decay process. This is a restatement of the equivalent laws of conservation of energy and conservation of mass.
Decay chains and multiple modes.
The daughter nuclide of a decay event may also be unstable, radioactive. In this case, it will also decay, producing radiation. The resulting second daughter nuclide may also be radioactive. This can lead to a sequence of several decay events. Eventually, a stable nuclide is produced. This is called a decay chain. See this article for specific details of important natural decay chains. An example is the natural decay chain of 238U, which is as follows. Decays, through alpha emission, with a half-life of 4.5 billion years to thorium-234, which decays, through beta emission, with a half-life of 24 days to protactinium-234, which decays, through beta emission, with a half-life of 1.2 minutes to uranium-234, which decays, through alpha emission, with a half-life of 240,000 years to thorium-230, which decays, through alpha emission, with a half-life of 77,000 years to radium-226, which decays, through alpha emission, with a half-life of 1.6 thousand years to radon-222, which decays, through alpha emission, with a half-life of 3.8 days to polonium-218, which decays, through alpha emission, with a half-life of 3.1 minutes to lead-214, which decays, through beta emission, with a half-life of 27 minutes to bismuth-214, which decays, through beta emission, with a half-life of 20 minutes to polonium-214, which decays, through alpha emission, with a half-life of 160 microseconds to lead-210, which decays, through beta emission, with a half-life of 22 years to bismuth-210, which decays, through beta emission, with a half-life of 5 days to polonium-210, which decays, through alpha emission, with a half-life of 140 days to lead-206, which is a stable nuclide. Some radionuclides may have several different paths of decay. For example, approximately 36% of bismuth-212 decays, through alpha emission, to thallium-208 while approximately 64% of bismuth-212 decays, through beta emission, to polonium-212. Both thallium-208 and polonium-212 are radioactive daughter products of bismuth-212, and both decay directly to stable lead-208.